All right. We're supposed to be on spring break, but some of you guys are just really anxious about the internal truss calculations. Several of you all have asked about it, so we're going to do a quick problem, quick being relative, obviously, for a truss, on how to figure out what the internal forces are on each of the members of our truss. So I've got this little truss that I've put together here. You'll notice that there is a roller support up here. There is a pin support down here, and we have forces being applied here, here, and here. Those are all forces being applied to the truss. Now, the very first thing that you're supposed to do is figure out where the reactions are happening and to put some labels on each of the joints. So because we have a vertical orientation of our two supports, this roller support will have a reaction in the x-axis. We don't know whether it's going to be left or right just yet, but we do know it goes in the x-axis because roller supports always have perpendicular reactions to the surface where they're mounted. Our pin support has this potential of having two reactions, both horizontal and vertical. So let's go ahead and put some labels on this. We're going to call this our first place where there is a force applied, A, then B, C, D, and E, just going in alphabetical order. Now, technically our first step from here should be making sure that it is statically determinate. I'm going to give you a hint on this. This one already is. And it's not what you guys are asking about, so we're going to skip that step anyway. The next step to come up would be the sum of the moments. So we're going to have the sum of the moments formula, which is equal to 0. And we have to identify where the moments are. Now, in this particular truss, our pivot point is at joint D, all the way down here. This is the pivot point there. So that means that we do have a moment at E, at A, B, and C. Because remember, moments happen in two places. They happen where force is applied or where a reaction happens that is not the pivot point. So we have a moment at A moment at B, a moment at C. We do not have one at D because that is the pivot point, and there is a moment at E. And all of these moments are supposed to add up to 0 if this is in static equilibrium. So remember, in the moments world, everything is either clockwise or it's counterclockwise. So we've got to pay attention to rotational directions, not linear directions. So when we look at A, and if we go back to our little cheat sheet version of this, clockwise directions go like this, and counterclockwise directions go the opposite directions like this, where everything is in relation to the pivot point. We look at this force right here, which is a horizontal force. It is above this pivot point. So that means we're looking at this one right here. That is clockwise. Now, clockwise is negative and counterclockwise is positive. So that is a negative 200 force multiplied by its perpendicular distance. So we've got this horizontal force. I need the perpendicular distance coming all the way down to here to where that pivot point is, which is this 30 feet that we've got listed right there. So that's negative 200 multiplied by 30. Plus, we've got a moment at B, and that one's right here, a little easier to see. This one is going up, and it's to the right of the pivot point, which is pointing at this. That's up to the right of the pivot point. That makes that a positive 175. And I need its perpendicular distance, which from here to get to there is 20, plus another 20 to get all the way over here, means that its perpendicular distance is 40 feet away. Plus, we've got another 50. This one is the exact same orientation as the last one. It is counterclockwise, so we're going to skip that. We know it's already positive, multiplied by its perpendicular distance, which is just 20 feet away, plus our last one, the moment at E. Now, our moment at E has a reaction force, so we're going to label it that way, reaction, at E, and it's horizontal, so that's a reaction force at E in the x-axis. This is what we're going to determine using our sum of the moments formula. So we know that there is a force a reaction force at E in the X, but we don't know what it is yet. What's going to come next is we're going to look at that perpendicular distance. Now, from here down to there, you might say it's not labeled. Well, yes, it is, because this is that. So this one is also 30 feet away, and we'll fill that in here. That equals 0. So now we just get our handy dandy calculator and start doing a bunch of multiplying. Negative 200 times 30 plus 175 times 40 plus 50 times 20. And I'm going to leave that other thing alone. This results in a positive 2,000 plus the reaction at E in the X times 30. Now, this is a silly problem that a lot of you guys are having. You're forgetting your basic Algebra 1 rules. If you cross the line, change the sign. So if this 2,000 is going over here, that makes that a negative 2,000. That's a terrible 2,000. A negative 2,000. And REX is still multiplied by 30. So my last step is to divide both sides by 30, which results that REX is negative, and it's 66.7 rounded. Now, if it's negative, what does that mean? That means clockwise. What does clockwise look like? It looks like this. If we are looking at that horizontal force that is above the pivot point, that's indicating this direction right here. So lo and behold, our REX, we finally know, points to the right at 66.7 pounds of force. Now, what's next? What's next is the sum of the external moments. So we're leaving the world of clockwise and counterclockwise. We're done with clockwise and counterclockwise. Now everything is up and to the right is positive, down and to the left is negative. Starting with the sum of all of the X forces should equal up to 0. How many X forces do we have? Well, technically we have 3. We haven't labeled this one down here, but there is a reaction at D in the X-axis. And we don't know what that is, but that's what this formula is going to tell us. We have a reaction at D, a reaction at E, and a force applied. See, that's why it's a different color. This is a force applied at A in the X. So we have these 3 forces all in play here. So I'm going to label all those out. I have a reaction at E in the X plus a reaction at D in the X plus a force applied at A in the X-axis. All have to add up to 0. How do you decide if it's positive or negative? It's not clockwise, counterclockwise anymore. If it points to the right, it's positive. And both E and A are positive. So we have a 66.7 plus RDX that we're going to find out plus our 200 is equal to 0. Okay, so RDX, that's the wrong letter, RDX will be equal to, when I add those two together, 266.7, and cross the line, I have to change the sign. That is a negative 266.7, and because this is a simple X force, that means it points to the left. So, take that back to here. And we're going to label this. It points to the left at 266.7. So what's left now? Well, now I have these 3 Y forces, and they're all right here on bottom. 2 of them pointing up. Well, what does this have to do? It has to point down. It's the only way it's going to balance it. And what is it going to be balanced as? Whatever the sum of those 2 are, which is 50 plus 175, or 225. We already know that's what it is, but I'm asking you guys to make sure that you can still document this process and understand how you get that. So here we go. The sum of the Y forces is equal to 0. There is a reaction at D in the Y-axis. There is a force applied right here at C, and there is a force applied at B. So we have a force applied at C and a force applied at B. All those add up to 0. RDY is what we'll find out. And again, our forces are 50 and 175, both going up, so both positive. So what happens? RDY is equal to, that's 50 plus 175, cross the line, change the sign, negative 225. Just like we assumed, that means it's pointing down. Confirming that's what this is. Now, finally, we've gotten to the point where you guys are like, where do I go next? I don't know where I'm supposed to start. The general rule of thumb is look at whatever joint has the least amount of stuff going on with enough information to answer all of your questions. The more you do this, the easier these are to figure out. Obviously, if I look at D, there is so much going on here. It's a mess. There are way too many things. I look at C. It looks pretty simple. There's just one opposing vertical force and two horizontal forces, but I don't know what either horizontal force is, so I can't start there. I can almost start here, and technically I probably could. We'll come back to that, but this one being the worst, look at all the weird things going on there. There's 1, 2, 3, 4, 5, 6, 7 forces at A, and we'll look at that later. If I look at E, what's going on at E? 3 things, and that's it. Just 3. So I'm going to start at E because it's the easiest one to look at. My free body diagram for E has this initial reaction force that we calculated with our sum of our moments as our very first step. The sum of the moments said that it points to the right at 66.7. There is this member and that member attached to E. Where are they going? E goes down to D, which is a Y force, and E goes to A, which is an X force on those members. Now, look at what you have. If I try to find the sum of the X forces, there are only 2. There is REX, and there is EAX. That again, from the member from joint E to joint A, and it is an X member. So these two have to add up to 0. The only thing we have on here is a positive 66.7. What does that mean? That EAX must point to the left to balance it. That's a negative 66.7 because if you cross the line, change the sign. So this is 66.7. We don't mark it as negative because the negative is assumed with the arrow telling us which way it points. Now for the fun one, the sum of the Y forces. What Y forces? There is only one. If there is ever a situation when there's only one Y force and we write out the formula, the only thing it can be is 0. So ED as a member has no force on it at all. So starting to transfer things back to here, this is 0. Wrong color. This is 0 force on this member. Now, EA had what? It had 66.7. Which way was it pointed? Go back and look. It's pointed at the joint right there. It points from the middle to the joint. So what does that mean? It points this way. Everything in a truss must be balanced if it's in static equilibrium. So if from the middle looking towards E, it points at E, then if I look from the middle towards A, it will transfer this way to point at A. Now again, there's still way too much going on at A. I'm not even going to touch that, okay? But I at least found out 2 members in this truss, which takes me back to I could also do some work with B. So let's figure out what's going on at B. At joint B, what does it have? It has one member going this way, one member going that way, and then it has some forces applied. It has a force being applied up, remember right here, at 175. We don't know what this force is, but I know that it goes from joint B to joint C, and it is an X force. What is this last member here? This is going from joint B to joint A. And now, is that an X or is that a Y force? Trick question. The answer is both. An angled member will always be made up of its 2 components, both the vertical and horizontal component. This is important because this is BA's Y component, and this will be BA's X component. Well, what do we do now? Well, we look at the sum of the y forces first, because currently I don't know anything about either x force, but the sum of the y forces has to equal 0, and there's only two. There's a force applied at B and the y, and there is BA's y component. These two have to balance and equal 0. So if those two balance and equal 0, then what are they? FBY is up, positive 175. BAY, I just found out, must balance that by pointing down at negative 175. So now I know another piece to this puzzle. Right here, this is 175 pounds of force. So what? Now what do I do? Well, recall that all the way back here, we had this little piece of information right there that we haven't used yet. It's time to bring in sine, cosine, and tangent. I know that that angle is 56.31 degrees. Now, if that was this angle, it also happens to be that angle. Those two will always be the same because they're corresponding angles of two parallel lines. What parallel lines? There's one right here and there's one right there. Here's my transversal. Go back to your geometry days. Those right here and there are congruent because they're corresponding angles. Okay, so that tells me that this little bitty angle in there is 56.31 degrees. So what? Now we do our sine, cosine, and tangent. We know that that is an opposite side and an adjacent side. So that will be tangent. Tangent of the angle that we are given, 56.31, is equal to the opposite side, 175, over the adjacent side, which is what we're about to find out, BAX. Put this over 1, time to cross multiply. So when I cross multiply, I'm going to get that BAX multiplied by the tangent of 56.31 is equal to 175. Remember that the tangent of 56.31 is just a number. So, side note, let's say that this is 10 and this equals 5x. In order to solve this equation, all I have to do is divide both sides by 5, and I get the answer because I have some variable I want to know the value of and some number that is being multiplied by it, right? Well, that's all we're looking at with this situation. Here is some variable that I want to know the value of, and this is some number that I know a value of. So I'm going to divide both sides by the tangent of 56.31. Blah, blah, blah. I don't want to write it again. So 175 divided by the tangent of 56.31 in the calculator tells me BAX has a positive 116.7 pounds of force. Now it's positive, it's X, therefore it points to the right. What does that look like on here? We just found that this points to the right. Thank goodness. That makes sense because when I started right here on this member and went down, how do I get back to it? I have to go to the right. So that confirms that I've done that part correct. It is 116.7. Now I can do my x forces because now I have one of the two. So sum of the x forces must equal 0. I have a BAX that I just found out and a BCX that I'm about to find out, and those add up to 0. This is 116.7 plus BCX equals 0. Cross the line, change the sign. That means it's negative 116.7, and if it's an x force that's negative, it points to the left. So lo and behold, we finally got another piece of information right here. It points to the left at 116.7. There's only one little piece to this puzzle that we have left, which is to find out what is that last force on BA. That's a member. I'm supposed to be finding out what are the forces of all the members. We have this part and that part of a right triangle. And if I have those two parts, all I need to use is Pythagorean's theorem. So, final step on this free body diagram, BA is equal to the square root of 116.7 squared plus my 175 squared. I don't need to worry about positive or negative because when you square them, they're always going to end up being positive. So I'm going to square my previous answer plus 175 squared, this is all under a square root, yields an answer of 210.3 pounds of force. Now, which way is it pointing? Well, you tell me. Which way are those arrows pointing that are in red? Down and to the right, which means this points that way at 210.3 pounds of force. Okay, this needs to go back to my original diagram. So all the way up here we go again. We just found out this, change to red because it's a force, a reaction at that, is 210.3 pounds of force. Which way was it pointing? Down and to the right. It pointed this way. Remember, every member has to have balance. So if it was pointed towards B on the other side, it will point towards A. What else did we find out? We found out this one was pointed left at 116.7 pounds of force. Where's the balance on BC? This time it's pointed towards the middle, so is this one. Well, now what? Well, now I can sit here and look at C, and I have enough information now to complete C. So let's take a look at C's free body diagram. C is extremely simple. There's a force applied, there's a member going up, a member going left, and a member going right. What are those members? This is BC, this is CD, and this one, I've already forgotten, is AC. I was going to guess that. And this is my force applied at C and the Y. Now, what is it? This was 50. Going which way? Up. We're going to skip the formulas this time because they're as basic as they can possibly get. If this one's going up and this is my only Y force that opposes it, this one must go down. At how much? 50 pounds. What did I find out from the other side? These were pointed towards the middle, right? Go back and look. That's what it was doing. They were both pointed towards the middle. They're right there. No, both those arrows are pointed towards the middle at 116.7 pounds of force. So this is 116.7 pointed to the right. What has to happen on CD? It's got to point to the left. At how much? 116.7. See, we didn't have to do hardly anything here. All we have to do now is just transfer what we just figured out to here. This is pointed down. This is pointed left. Those are in the wrong colors. This is a good Monday, isn't it? This is pointed down. This is pointed left. This is at 116.7 again. This was at 50. And what's going to happen? Take a look at AC. AC is this vertical member right here. I've got one part of it pointed down. The other part must balance and point up. Look at DC right here. This is pointed towards the middle. So does this one. It has to. What's left? The only thing that we have left to figure out at this point is what's going on with AD. How are we going to figure that out? Which one do you think looks easier to mess with? A, which has a ton of forces, or D, which has a lot, but we've already got all of them except for one filled out? I like this one. It's got the least amount of work to do on it. It looks complicated at first, but it won't be that bad. So let's come all the way down here and draw our last free body diagram for this particular problem. D has a reaction force this way, a reaction force this way, a member force this way, a member this way, and an angled member this way. It looks like a lot, but let's remember what we know about this. That's 0, right? That was all the way back here. We said when we started off with E, there was not an opposing Y force. That's this. It is 0. What else do I know? I know that the horizontal reaction is 266.7 to the left. So add it on. 266.7 to the left. What else do we know? Looking back here, we've got this piece of the puzzle. 225 pointed down. Let's add that one on. This goes down at 225. What else do we know? We know this information right there. From the perspective of D going towards C, it is pointed to the right at 116.7. 116.7. Well, what's missing? The only thing missing left is this member from D to A. Now, is that a horizontal or vertical force? Again, trick question, it's both. It has a horizontal component and a vertical component. Now, what do I know? I know that this force right here is 0, so I can basically ignore it. So how many other y forces are there? This one and this one. What did we just determine about when there are only two forces in the same alignment, either vertical or horizontal? They have to oppose and they have to be the exact same magnitude. So this will have to point up. At how much? 225. If you want to do the math for it, the sum of the y forces is equal to day plus rdy, and we've got one negative 225 that moves over to a positive 225 because cross the line, change the sign. Well, what else is left? Look at my x forces. We'll go ahead and work this one out. There's a little more stuff going on here. The sum of the x forces has to equal 0. What do we have? A reaction at D in the x. We have a force on the member DC in the x, and we have DA's x component. I got an extra equal sign in there. These three have to add up to 0. What do I know? 266.7 to the left. That's negative. DCX, that's going to be 116.7 positive because it's to the right. What am I going to find out? DA's x component. Okay, so 266.7 is negative. 116.7 is positive. There is a difference of a negative 150. Cross the line, change the sign. DAX is a positive 150, which means it points to the right. Does that make sense? Yes, that's the good thing about these things. They better make sense because we can check as we go along. I've got 2 of 3 sides of a right triangle again. Which way does it point? Up and to the right. What is that magnitude? I've got 150 and 225. I'm at my second to last step. I want to know what DA is. Pythagorean's theorem says square root of 150 squared plus 225 squared. So punch that into the calculator. 150 squared plus 225 squared under a square root symbol says that DA is 270.4 pounds of force. This is 270.4 pounds of force. Where does that go? All the way back on our original diagram, changing colors because these are all reaction forces. From D, it pointed up and to the right at 270.4 pounds of force. Where's the balance? They both point towards the middle. It goes like this. I never have to look at A. I've filled in every single member with their force and which way their forces go. Are they pushing out because they're being crushed? If they are, that's compression. Are they holding in and pulling in because they're being torn apart? That's tension. So this is tension. This is tension. These are pushing out. They're compression. This is pushing out. That's compression. That's it. Now, the only other thing we have is this little 0 in here, and anytime you have 0, the assumption is that it's under tension, even though there is no force. That completes it. We're done. We figured out all the internal forces on this particular truss. So, here's hoping that helps. If not, always post questions and I'll get back to you. Thanks.